Okay, so I wanted to do two more examples of related rates problems 3 and 4 from the PDF. And there's a couple tricks I wanted to show you in here. Number 3 says a conical cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? And so the first thing you might recognize is that this is a cone, and you might recall what the formula for the volume of a cone is 1/3 pi r squared h. And maybe you look at that and you're like, that's a lot of variables for us to control in one calculus problem when we're not even in multivariate calculus yet. And that's a shrewd observation if so. There's a trick with cones specifically. Cones, I think, are the only formula that has two quote unquote variables on the right hand side of it that we'll use. And if you think of what's a cone, well, a cone can take on different shapes. You can have cones that are tall and skinny, and you can have cones that are short and wide, and you can have cones that are somewhere in between that are. And what you should know about these cones, because a lot of time we'll talk about them being filled up to a certain point with water, is that the cones have two dimensions. They have radius and they have a height. But those things exist in fixed proportions inside the cone. So if I have a cone and its ratio of its height to its radius, let's say h is equal to 3 times r, that's going to be true throughout the cone at any level that the water is filled up to. And oftentimes in these cone problems, you'll have to use that knowledge that this height, the ratio between that height and that radius is the same as the ratio between this height and that radius. That this height and this radius has the same ratio as this height and this radius. And very infrequently will you get one as simple as h is equal to r. But being that this is the first time we've done this, that's what it is. So 10 centimeter tall and 10 centimeter radius, which means I can substitute r for h or h for r, and I get the decision of which to do for which. And because they give me a water level rising at 2 centimeters per second, I'm taking that to mean dh dt, which is 2. So I'm going to plug in for dh. I'm going to plug h in for r to eliminate r instead in this case. So now v is equal to 1/3 pi h cubed. And I'm going to take the derivative of the whole thing with respect to t. And I get dv dt is equal to pi h squared dh dt. And then it's just a matter of substituting what for what. 2 is dh dt. 8 is h squared. When I do all that, I get pi times 8 squared times 2, which is 128 pi. And then the unit is dv dt, so it's volume. So this is centimeters cubed per second. Boom. All right, next one is a spherical balloon is inflated so that the radius increases at a rate of 2 over r centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? So what do we remember about the volume of a sphere? Well, that formula is volume is equal to 4/3 pi r cubed. So now I want to know about how is that changing with respect to time. And I get dv dt is equal to 4 pi r squared times dr dt. And one little tangent or aside is that this formula, 4 pi r squared, the rate of change of the balloon, is the same as the surface area formula for a sphere, which I don't know if that's a coincidence or that happens in every three-dimensional shape, that the derivative of the volume is also equal to the formula for the surface area. It's a fun one to think about. I'm not going to answer it for you. What do we need to plug in? Well, I need to plug in 2 over r for dr dt, and I need to plug in So well, let's do that first. So I'm going to get 4 pi r squared times 2 over r, which is then going to simplify to 8 pi r. And now I can substitute in the 4 for the r, and I get 32 pi. And since it's volume, it's going to be centimeters cubed per second. Hopefully that's helpful, because these problems are going to get trickier, quicker, and just seeing the framework for one like that can be helpful.